Greetings. In this one, we will be talking about the orbit stabilizer theorem. And the first thing that I want to show is basically we want to find a mapping that goes from the cosets of the stabilizer subgroup of G in G to the orbits of the element X in G. Of an element X in G, where our group action concern is group G acting on set capital X, and these x's here are lowercase x. On the left, G sub x is the stabilizer of X, and on the right side, G dot lowercase x is the orbit concerning that same arbitrary element X in the set capital X on which the group G acts in this group action. So if I can prove that this is a bijective mapping, then I can conclude that the index of the stabilizer G sub x in the group G is equal to the magnitude of the orbit of G dot x, and that is, or as G acts on that element X, and that would give some results that we want to get to. So to prove it's bijective, first thing is to see if it's surjective. So any element of this is basically written as G x. I might drop the dots in a second for saving space and so on, but in any way, G dot x, and it tells us, well, it's surjective if every of these elements in the codomain can be mapped to by something from the domain. Well, that's of course true, because for every G dot x we have a G in G that will result in this G dot x, so that's trivially proven. And then for injectivity, we can consider that, I will just use what we already wrote. I will consider some two elements G and H from the group G that acts, and I will say that Gx is Hx. I might drop the dot, but I still mean the same as if the dot was there or not. The same is meant. So if G acts on some element X in the set X, or H from G acts on X, that if that is equal, then what we have is basically, I can manipulate this a little bit, and I can say G inverse on the left of both sides. So I can have X equals G inverse H times X. And what this equation says, that it's equivalent, these two things, or it actually implies. I can just talk about the implication, that's enough. So, well, that implies that X equals G inverse H X if I put G inverse on both sides on the left. And that says that G inverse H with X equals to still X on the left side. That means G inverse H is in the stabilizer, because that's what the stabilizer does. It's elements of G that preserve the X unchanged. And for that reason, we can conclude, first what I could write is also this. I can do the sort of H on both sides on the left. The H is in the coset G times G sub X times the stabilizer of X. And what I can also say that basically H as a coset equals to the G left coset of the H left coset of stabilizer X equals to the G left coset of stabilizer X. So G and H have the same function here. And by that I basically prove surjectivity. And with this, we can conclude that this mapping is bijective. Both injective and surjective were proven, and that's a very, very powerful information, because we can now conclude that, and we can write it down, that basically the G index, the G sub x, the stabilizer's index, is equal to the magnitude of the orbit of X. And that's a very useful thing, because the index as follows basically talks about the amount of the cosets that the subgroup has in the group G sub X. The stabilizer of X in G is a subgroup of G, and this by Lagrange theorem is also equal to basically the ratio of the magnitudes of the two. So the ratio of the G and the G sub X, but that is still equal to the G dot lowercase x. So that basically tells us, and if we just, I will not rewrite it anymore because we have no more space here, But if you look at this equation now, well, the left side I wrote using Lagrange theorem, and on the right side we got that other basically the amount of elements in that arbitrary orbit with G and some element x from x. That basically tells us that I can multiply now on both sides by the amount of elements in the stabilizer, and what it tells us that the cardinality of the group G equals to the cardinality of the stabilizer subgroup times the cardinality of the orbit set for that element x.